On the last video, we evaluated the line of sight and how the line of sight changed with a change in elevation. We next want to take a look at how the arc length, or the distance out along the surface of the Earth, changes with an increase in height of the observation point. And that brought us into the differentiation of inverse trigonometric relationships, which we're going to talk a little bit about. And then we're going to solve this problem about how the distance to the horizon changes with a change in elevation. So the problem that we worked, we showed that L was equal to r plus h squared minus r squared. And we calculated its derivative, showed how dl dh, showed how L varied with h in order to answer that question. Now we're looking at the arc length along the surface. So we want to know how this arc length, S, changes with a change in elevation. So we know that S is equal to r theta. We want to evaluate ds dh. And so we're going to have to evaluate the derivative of this inverse cosine, which in this case is the cosine of inverse cosine of theta. Cosine of theta is r, the side adjacent, over the side opposite, r over r plus h. So we have to differentiate the inverse cosine of r over r plus h. So this is what we have to differentiate. In other words, what is d theta dh, and specifically how does the arc length ds dh vary with h. So we have r times d theta dh. This is our theta right here. This is our r over here. It's a constant. So we're just differentiating the inverse cosine, r over r plus h. This is something that we haven't done before, and we've got to do this in order to figure out how the arc length changes with changes in height of observation. So we're going to start by looking at the cosine of theta. Cosine of theta will define that as being equal to some value x, so that the inverse cosine is just equal to theta. And what we do is we take the derivative of this expression here, but we do it in a chain rule fashion. We differentiate the cosine with respect to theta, but then we differentiate theta with respect to x. So carrying out that differentiation, we know that the derivative of the cosine of theta is just equal to minus the sine, and the derivative of theta with respect to x, we have that here. dx dx is just 1, dx by dx. We just get 1. So we end up with d theta dx is equal to minus 1 over the sine of theta. So what are we going to do with this theta? I mean, we don't have sine of theta, we have cosine of theta is equal to x. What are we going to do with this? Well, recall this basic identity here. Sine squared theta plus cosine squared theta is equal to 1. And we're just using this triangle over here. Sum of the squares of the two sides is equal to the square of the hypotenuse. So we know that this is true. We have an expression for sine of theta. Think about this for a minute. Pause the video and think about how we can change this expression with a sine in it to one with a cosine in it. And remember that the cosine is equal to x. Okay, so I assume you took a minute or two to figure that out. We have that theta is equal to a cosine of x, and d theta dx is equal to the derivative of the inverse cosine of x with respect to x. And this is just what we found. found that d theta dx is equal to minus 1 over the sine of theta. And I asked you to think about this relationship and how we can relate it to our problem. And so, using this identity, we see that the sine of theta is equal to 1 minus the cosine squared of theta to the 1/2 power. And so cosine of theta is just equal to x by definition. So what are we going to do here? So again, this is all a bit of review. We have cosine of theta is equal to x. Bit of redundancy here, leading you in that direction. Cosine of theta is equal to x. Well, this is just going to give us that minus the sine of theta we have up here is just going to be equal to minus 1 minus x squared to the 1/2 power, where x is equal to the cosine of theta. So our d theta dx, in other words, the derivative of the inverse cosine, is going to be equal to minus 1 over 1 minus x squared to the 1/2 power. Okay, so that's pretty much how you go about the differentiation of the inverse cosine, which we just went through. Now we want to take a look at that problem. We want to see how the arc length varies as we change the elevation, as we change our height of observation. If we move up a meter, down a meter, how is that going to change the length along the surface? How is that distance going to increase? So just substituting in, we have r ddh of the inverse cosine of r over r plus h. We're going to do this in a chain rule fashion. We'll let r over r plus h equal u up here, so this is going to be equal to u. Then we're going to do it in a two-step fashion. We'll have ds dh is equal to ds du. That's our u over here. And then we have to calculate the derivative of r over r plus h. So we have this is equal to d r theta du du dh. Sorry, this should have been a capital R. Something going on outside there. And so we get an r d, and then this is the inverse. Remember, theta is the inverse cosine of u. Okay, so we're taking d theta du here, and then we're multiplying that by du d theta, du dh. Okay, so d theta dx, we've already figured this out. It's equal to minus 1 over 1 minus x squared to the 1/2 power. And then as we just outlined, we have ds dh is equal to, we're going to do this in a chain rule fashion. We differentiate s with respect to u, then u with respect to h. We have the derivative of r theta with respect to u, du dh. And so we're just kind of repeating that for reference. U again is equal to r over r plus h. And so we have this relationship using the chain rule approach. So let's evaluate. First, we're going to have to evaluate what du dh is. So hopefully you're comfortable in taking this derivative. If you take this derivative, you should get that dr over r plus h is going to be r over r plus h, the quantity squared. Just using our power rule and chain rule. So plugging in these different quantities, we have ds du and we have du dh. So our ds du is, and we have this constant r, is minus 1 over 1 minus u squared to the 1/2 power. Our du dh is equal to, we had a minus sign in here, is minus r over r plus h, the quantity squared. So substituting back in for u, which is u squared, we have minus 1 over 1 minus r squared over r plus h, the quantity squared to the 1/2 power, times minus r over r plus h, the quantity squared. Now what I'd ask you to do, and again you might pause the tape and fiddle around with the algebra here, but pull out this r plus h squared in the denominator of this term. That's going to give you an r plus h squared over r plus h squared, right? You're going to pull out the r plus h squared. So that we get ds dh is equal to, we have minus r. We pulled out our r plus h, so we have 1 over r plus h, but we have an r plus h up here in the numerator. We just replaced 1 by r plus h over squared over r plus h squared. We pulled out an r plus h squared, which was to the 1/2 power, so we get 1 over r plus h. And this is all times minus r over r plus h, the quantity squared. Okay, so taking that r plus h and flipping it over, we get r plus h minus r plus h times r. We squared the term inside here, r plus h squared. Get r squared plus 2hr plus h squared minus r squared. I could have put a left parenthesis around there. Times minus r over r plus h, quantity squared. And these r's cancel out. So we end up with r plus h canceling this one out. So we end up with r squared over r plus h times 2hr plus h squared to the 1/2 power. And we could argue that since r is a lot greater than h, our ds dh, all this quantity over here, can be simplified to r over 2hr to the 1/2 power. In other words, this is close to r, so we cancel out one of these r's, and we can ignore this because it's a relatively small term. So we end up with 2hr to the 1/2 power. So that's our ds dh. So, and this is what we were after. We wanted to know how the arc length, how the distance along the surface changed with a change in elevation. And so evaluating that, using a radius of 6,370,000 meters and a height of 100 meters, we get a ds/dh of 178.462 meters per meter, change in h. I should have added that in there. And then this ds/dh, this is an explicit calculation using not making the simplification that r plus h is approximately equal to r. This is using the simplification. We get 178.466. So you can see that these two are pretty close together, so this is a lot easier to do than this, and we don't really have much error. And also, just as part of the comparison, let's think back to the change in the line of sight with respect to h. This is, remember, we got r plus h over 2hr plus h squared to the 1/2 power. This is equal to 178.468. So the increased line of sight is slightly more than the increased surface distance ds/dh. So this is basically the answer to our question: how much does the distance out along the surface change with an increase in height of 1 meter when we're standing at 100 meters above the surrounding area? Okay. Well, next time we're going to talk about, have a little bit more on the derivatives of inverse trig functions, and we'll take a look at some useful relationships using triangular representations of trig functions.